projection on X. So this is X dot Y. So it becomes a scalar. And do we have any other operation of vectors? Yes, we do have. Outer product. So in electromagnetic, we have X vector cross Y vector equals Z vectors. For example, in electromagnetic, we have pointing vector. Pointing vector equals E electric vector cross magnetic vectors. So the result, the output of the outer product is a vector. So right now we can see that after operation of addition, we have output a vector. And after scalar multiplication, we have an output of vector. But after inner product, we have an output of scalar. And after the output of the outer product, we have a vector output. So in this course, we will only cover these three. We will only cover these three vector operations, and we will not be going to discuss outer product in this course. Okay, so basically we will only discuss the first three operations. But right now we have a definition of addition and the scalar multiplication. Okay, so as long as we have the definition of addition and the scalar multiplication, so then a vector space, the elements in this vector space. So right now, a vector space is a set of vectors. So the vector space is comprised of many vectors. So here I have a vector space. For example, this is a vector space V, and inside this vector space I have X, Y, Z, and etc. and many vectors. Each one element is the vector. Okay, so for these vectors in this vector space, we will have the first property V1. For all X and Y in V, we have the commutativity law of addition. So we can exchange the order of two vectors under addition operation. Okay, so we have X plus Y equals Y plus X. The order is not important, but in some operation the order is important. For example, in the future you will see X and Y. Actually, in this textbook, we denote this as inner product. So it will be equal to X times Y bar if X, Y are in the complex field. So then in this definition, YX, the inner product of YX will be equal to YX bar. So these two the result of these two operations will not be identical because it's operated in the complex field, and the definition of inner product is not linear. It's not real linear. Okay, so we will discuss this in chapter 6. So right now, for the regular vectors and for the regular addition operation, then we have two vectors in this vector space, and the sum of the two vectors are identical, even though the order is different. Okay, and then we have associativity law of addition, so which is pretty much the same as these A properties. So we have S plus Y first plus Z will be equal to S plus Y plus Z first. Okay, so we have associativity law. And then VS3 define the identity element of addition, which is that, okay, there exists an element in V denoted by 0 such that the addition of 0 and any vectors will be equal to the vector itself. So here, in the vector space, 0 vector must exist. 0 vector must exist, and 0 vector will push. If I 0 vector add any vectors in this vector space, it will be equal to the vector itself. Okay, so 0 vector identity vector of addition operation is defined. Then VS4, for each element X in V, there exists an element Y such that X plus Y equals 0. So what does this mean? VS4 means that X plus Y equals 0. So then we have the additive inverse of X under addition operation. So we have additive inverse of X under addition operation, and we define this inverse vector as Y equals minus X. Okay, Y equals minus X. So minus X is the inverse, is the additive inverse of X. Okay, so we define this. So we denote the inverse, additive inverse of X as minus X. Okay, so VS4 tells us we have additive inverse of any vector. Okay, and then VS5 states that for each element X in V, any the scalar 1 times vector itself will be equals vector itself. So there's no stretching, there's no shrinking. So we have the scalar multiplication of 1 times X equals X. Okay, and also VS6, if I have two elements in the field F, A and B in the field F, so we have the definition of multiplication of these two elements in field F. And each element X in V, we have A times B, the scalars, the multiplication, we multiply these two scalars first and the times vector. So we have the scalar multiplication, which will be equal to B times X. We do the scalar multiplication first and then do another scalar multiplication, because BX, output of BX is a vector also. Okay, because the X vector has been stretched by B times. So it's also a vector here. And then so we have a scalar times a vector, so it's also a scalar multiplication. So we can multiply the scalar first, then do the scalar multiplication. And we can also do the scalar multiplication first and do another scalar multiplication. And it will not change the result of these operations. And the VS7 says that for each element A in F and each pairs of elements X and Y, vector X and Y in V, and then we have the distribution law. So A times A X plus Y will be equals to A times X plus A times Y, which is very straightforward to us. And the VS8 is that, okay, if I have two scalar elements, A and B, and I have a vector X, so the scalar, we have the addition of the scalars first and times the vector, so we have the scalar multiplication, and then which will be equal to A times X plus B times X. So here, actually, for this A operation, for these 8 facts, actually, we are very familiar with. So with these A properties, it forms a linear space, or we call it as a vector space. So right now, we are going to give some examples. Okay, so for two dimension, actually we have the plane coordinates. We have the 2-dimension coordinate. So I have x-axis and y-axis. So this is the two-dimensional geometric. So for any vector here, u vector, I have a1, a1, b1. So I have a coordinate of a1, b1. Okay, and for another vector here, v, I have another coordinate a2, b2. So this is the vector for two-dimension vector space. Okay, so here I have, for example, here I use a1, a2. So a two-dimension vector x equals a1, a2, and the a1, a2 belongs to a field. Okay, and for this field, this a1, a2, in fact, of course, in geometry, both a1, a2 are real numbers. But in many other applications, a1, a2 can be complex numbers. They can be complex numbers, especially in the convocation theorem. Okay, so and then I can also have three-dimensional vectors. So here I have three-dimension coordinates, x, y, z. So any vector will contain three elements, a1, a2, a3. For geometry, we will have three real elements, a1, a2, a3. So it is a three-dimensional vector space. So y is in the three-dimensional vector space. And also, we can extend this dimension to n dimension. So we can have z, which is an n-dimensional vector. So I have a1, a2, a3 to an. I have n elements here. So then, in this system, we have n-tupled. So each one, we can call it as entry or components. So then we can extend the vector to n-dimensional vector space. And each n-dimensional vector space will have n-tupled column vector. Okay, so AI can be real or complex number, just as I mentioned. But in your geometry math, you only learn all the entries should be real number. But in fact, they can be either real or complex. Okay, so in these n-tuple column vectors, then we define n-tuple vectors. We define the addition of two vectors. So I have x equals a1, a2 to an, and y equals b1, b2 to bn, and we can add these two vectors together. So we will add each individual element together. So a1 plus b1, a2 plus b2, a3 plus b3. So here we can know it easy because for u vector here, I have a1, a2, a3. And for v vector here, I have b1, b2, b3. So a1 represents the projection of this vector on x-axis. a2 means use projection on y, and a3 means the use projection on z. So we will not add a1 to b2 because they will be different. They will have different meaning here. Okay, so a1 cannot add to b2 because they are on different axes. So we will only do the addition on the same axis here, a1, b1, and the addition of a2, b2 on y, and the addition of a3, b3 on z. Okay, so we have the definition of addition of two n-dimensional vectors. And for the scalar multiplication, each element has been extended. It has been extended by c times. So cx will be equal to ca1, ca2, ca3 to can. So here, we have the definition of scalar multiplication, and we also have the definition of addition. And now we have to define if two vectors are identical. So if I have UV vectors and we say they are equal, if and only if all the elements are the same at all axes. So I will have A1 equals B1, A2 equals B2, A3 equals B3, and AN equals BN. So all the elements, all the entries AI equals BI in these two vectors. So then I can have two identical vectors. So here, B, V here, and V will B1, B2, B3. We have the same coordinates. We have the same coordinates. So these two vectors are identical. Okay, so right now, so we have the conventional definition of vectors. So the vector can be either a column vector, so we write the vector in the column format. And also we can have it as a row vector. We write this vector in the horizontal format. So this is the, so we have two definitions of vectors. One is column vector and the other is row vectors. And in between these two vectors, we can say V will be equals to the transpose of U. Okay, so if we just rotate the direction of the vector from column to row, then we say we denote it as U sub T. So this is the transpose. Transpose of a vector. We have the transpose of a vector. And then in the future, we will also define the transpose of a matrix. So we just exchange the order of the row and the column. Okay, so we have the transpose of vectors. So we can transpose a vector from a column vector into a row vector or vice versa. Okay, so and so for this vector, just as I mentioned, so this vector can be either real number vector or complex number vectors. So here, any element we claim it as a vector in a vector space must follow the A properties of VS1 to VS8. And here the definition of vector is no longer the same as how we define a vector in physics notes, because any mathematical system, if it can follow this, if it can have these A properties, then it forms a vector space. So for example, for a polynomial, so in mathematics, actually a polynomial is just a polynomial. We have n-degree polynomial, but is it a vector? Actually, if you verify VS1 to VS8, you can see that because we have the definition, of addition. That is, if we add two polynomials together, we will only add the coefficients with the same power. With the same power. We cannot add an to bn minus 1 because they are not with the same power. Okay, so we can only add the coefficients of the same power. So we define the addition. We define the addition of two polynomials. So fx equals an times x to the power of n plus an minus 1 times to x to the power of n minus 1, etc. to a1 times x plus a0 times x to the power of 0. And the g sub x looks like bn times x to the power of n plus etc. to b0 times 1 or times x to the power of 0. So when we add these two polynomials together, we only add the coefficients of the same power. So we define the addition. Okay, and we define the scalar multiplication c times fx equals c times an times x to the power of n plus c times an minus 1 times x to the power of n minus 1, etc. So we only multiply the coefficients of all the power by C. Okay, so we have a scalar multiplication. So here, we can just imagine that. We can just imagine that for a V, for example, for a three-dimensional vector space, I have U, which will be denoted as A1, A2, A3 in this X, Y, Z coordinate. And what does it mean? Actually, we can write as from our high school math. We have A1 times X vector, unit vector of X, plus A2 times unit vector of Y, plus A3 times unit vector of Z. So then we can represent, we can just take the coefficients out of this expression and denote it as A1, A2, A3. Denote this vector by this row vector. So in reality, it must be A1 times X plus A2 times Y vector plus A3 times Z. So with the same idea, if I have for the n degree polynomial, so I have an times x to the power of n plus an minus 1 times to the power s to the power of n minus 1, etc. times a1 times x plus a0 times x to 0. So if we consider this power of x as some individual axis in an n plus 1 dimension vector space, then we can just take the vector as an minus 1 to a1 and the a0. We just take the coefficient out from this polynomial, and then it can form a n plus 1 tupled vector, row vector, or n plus 1 tupled column vector. Because here we have n plus 1 element or entries. So in this format, actually we know it's a vector, but it's the column vector representation of a n degree polynomial. So in this scenario, actually we know this is this kind of format form a vector space so as to this polynomial. So right now, the vector space is no longer the definition of a physical system. In mathematics, it can have many other formats. Okay, so here we can verify that for such a polynomial can satisfy VS1 to VS8. So the polynomial function form a vector space. Okay, so right now the vector is no longer a vector that we are familiar with. Okay, so here for the polynomial we can also have a vector space formed by all the polynomials. And then here for a matrix. Okay, if I have an m by n matrix, which means that I have m rows and n columns. Okay, so matrix m by n, we will have m rows and n columns. So here for the m by n matrix, so right now I have a matrix A11, A12, A132, A1n, A21, A22. So I have m rows and n columns. And then for the ith row, then we can have the vi, which is a row vector. I can have ai1, ai2 to ain. So it's an n-tuple row vector. And for the jth column, I can have uj, which will be consist of a1j, a2j to amj. So here, this is an m-tupled column vector. So here, for an matrix, actually we can have m row vectors and n column vectors. So here, so we can have this this definition. Okay, and typically we denote aii. That is the diagonal line. So maybe it will be look like this, or maybe it will be look like this. It depends on whether m is larger than n or not. Okay, and if I have, of course, if I have m equals n, then we have a square matrix. We can have a square matrix. And also, in the vector space, VS3, 0 is very important. So we denote 0 vector in an m by n matrix, which equal to 0. All the elements, all the entries in this m by n matrix are all 0. So that is the 0 matrix of m by n matrix. Okay, so we define the 0 matrix. So this is a 0 matrix. Okay, this is a 0 matrix. Then, if we define A as A11 to A1n, AM1 to AMN, so then typically, for simplicity, we will write it in this form, Aij. I is from 1 to m, and j is from 1 to n. Okay, so we will just write A, we can express A matrix as Aij, and the B equals B11 to BM1, B1n to BMN. So we can also express it as Bij. So if I have A matrix equals B matrix, which means that all the elements at the same position are identical. All the elements are identical at every position. Okay, so we have the definition of the matrix. So then we can go back to VS1 to VS8, and we can verify all these A properties hold. Okay, all these A properties hold with our conventional definition of matrix addition and the matrix scalar multiplication. So for example, I have two vectors, just as I mentioned there, A and B. So I have matrix A, which is represented by Aij, B, which is represented by Bij, and the A plus B will be denoted Aij plus Bij. We do the sum of entries at the same positions. And we define CA becomes CAIJ. Okay, so we have the definition of addition of two matrices and the definition of the scalar multiplication of a vector. Of a matrix. Okay, a scalar multiplication of a matrix. So we have this definition and then VS1 to VS8 hold. Okay, so, but sometimes if we have a definition of addition and scalar multiplication, but they cannot form a vector space. For example, for this case, I have vector A1, A2, two-dimensional vector. And then we have A1, A2 belongs to this set. B1, B2 belongs to this set. But if we define addition, A1, A2 plus B1, B2 as A1 plus B1, but A2 minus B2, which is different than our conventional addition of two vectors. And also we have a scalar multiplication, which is identical to how we define the scalar multiplication. So then here you can easily find that VS1 doesn't hold. VS1 fails because if I have X equals A1, B1, Y equals A2, B2, then X plus Y will becomes A1 plus A2. B1 minus B2. But Y plus X will becomes A2 plus A1. But B2 minus B2, B1. B2 minus B1. So we can easily find that these two vectors, this addition of two vectors are not identical to each other. So VS1 failed because the commutative law doesn't hold. So VS1 doesn't hold, VS2 doesn't hold, and VSA doesn't hold. So you can find that S for the definition of addition and the scalar multiplication, like this, it cannot form a vector space. Okay, let's stop here and take a break for 10 minutes.我这样讲会太快吗？还可以哈，还可以听得懂哈。好。 OK， 好，那我们开始吧。那各位如果说去EE-Class， 现在可以看到说，我们已经开始直播了。好，我们已经开始直播了。那所以各位同学其实可以选择自己在家里面看直播。好，你们可以选择自己在家里面看直播。不过通常是这样子啦，我就说过，我在第一节就说过，第一节为了要加签，所以我们这个座位都不够啦。一旦加签成功之后呢，就开始出现了电动了。然后后来呢，因为随着我们上课继续上下去的时候，那自由电子会越来越多，电动就越来越多。好，所以呢，因为我们这个原子核的不够力，好，所以呢，我们的自由电子会越来越多。好，那到了学期末的话，大概一般而言，过去的情况大概是剩下1/3左右。好，所以那我没有很在乎说你们有没有来上课，重点是如果你们有问题要问，好，那要问的话，当然是在课堂上面问会比较方便。好，那如果说在家里面看的话，那你要问问题就比较不方便。好，那以前我在念博士班的时候，我们的学校实际上教室里面是有电话的。然后呢，我们那时候因为在90年代还没有 Internet 没有那么发达，那时候只有 email 而已，只有 text mode 而已。那所以那时候其实没有直播，但是我们学校我念的南加州大学跟南加州很多的公司有合作，所以他们的课程呢都是利用闭路电视的系统，用电视系统去到各公司的会议室。那想上课的人就直接到会议室去上课。那时候呢，他们学生有问题的话，那也算是一种直播。那学生有问题的话，就直接 call in 进来，好，直接 call in 到教室里面给教授问说，直接问问题。好，那我们的直播呢？我们这个情况其实会越来越，就是各位可能一开始可能只是慢了1-2节，然后慢慢的越慢越多，3、4节、5、6节，到最后呢就干脆就不看了，自己看课本了。好，所以这个部分就是说，但是我的看法是说，如果你们有问题就要来问，好，那能够及时的得到帮助是最重要的。那你如果落后很多的话，到最后其实你自己要负责任。好，那所以我并不会点名哈。首先我跟各位讲，我不会点名，好，所以不用担心说，你没来上课会不会有平常成绩？我们的成绩里面没有算平常成绩，好，就只有看你的期中、期末考而已。好，请各位同学知道注意一下这一点。好，会不会现在就有自由电子出现了？好像没有哈。OK， 好。Okay, so we in the next hour, we discuss about the property of vector space. And right now, we're going to begin the very tedious part of this course, that is the theory and the proof. So we have a lot of theory and we have a lot of proof in this class. So here we have theorem 1.1, which we call it as cancellation law for vector addition. So here, if I have three vectors x, y, z, and they are all in a vector space V, so we have the definition of vector addition, and we have the definition of scalar multiplications, so that s plus z equals y plus z. If s plus z equals y plus z, then s plus x equals y. So actually, very intuitive. We can just cancel these two. Cancel these two identical vector z and z here, so we can get s equals y. But right now we have to follow the strict math. So all the operations should be based on vs1 to vs8. So right now we have to prove it by using vs1 to vs8. Okay, so in this scenario, then we have to first, from vs4, we know we have an additive inverse vector of any vector in vector space V. So here, if we assume U be the additive inverse of Z, so then we have U plus, we have Z here follow the note here is V. Sorry. So Z plus V equals 0. Okay, this is by VS4. So then we will begin our proof by using VS1 to VS8. So here I can have X equals X plus 0. So this equation is based on VS3. Okay, then I can replace 0 by using Z plus V. So I can plot X plus Z plus V. So this is from VS4. Okay? And then we can apply associative law so that we can reorder the addition operation by using this associative law. So the associative law is VS2. And then by assumption, because here from the theorem we know S plus Z equals Y plus Z. So we can replace S plus Z by Y plus Z plus V. So that is by assumption. Okay? So then we can apply the associative law again. Then we have Y plus Z plus V. So that is VS2. Then we know Z plus V equals 0. So that's from VS4. And then we have the result equals Y. That is from VS3. So then we can have X equals Y. So from the strict mathematical point of view, we have to prove it by using these many steps. But by intuition, S plus Z equals Y plus Z. Just cancel them. Okay? But we have to prove it by using VS1 to VS8 here. So here we have the cancellation law. And then we will begin to discuss the corollary one. So right now, actually, in a vector space, we define that in this vector space, it must contain 0. 0 must be contained in this vector space. But is it unique? So is it possible there exists another 0 vector we denote it as 0 prime, that such that 0 is not equal to 0 prime, but X plus 0 prime equals X in V? Is it possible? Is it possible? Here we are going to prove the uniqueness. So whenever you see a problem that asks uniqueness, then you can prove it by using contradictory approach. So whenever it asks, is it unique? Then we will assume 0 is not unique. So that 0 is not equal to 0 prime. Okay, but 0 prime A also has this property, S plus 0 prime equals X. But for the real 0, we know that it will be equal to X plus 0. So then we can use cancellation theorem to cancel X, and then we get the result, which is 0 prime equals 0. So this is contradictory to our original assumption, which means that this assumption is wrong. Then 0 must be 0 prime, which means the 0 vector in a vector space is unique. Okay, so we prove it by using contradictory approach. Okay, so is there any problem in this proof? 你们觉得这个证明有错吗？依照严格数学来讲，这个证明是错的。这证明不完备 ，is not complete. Why is that? Because here we are using cancellation law. But in cancellation law, we say x plus z equals y plus z, such that x equals y. But do we say z plus x equals z plus y, x equals y? No. In cancellation law, we haven't proved it yet. So here, can we apply cancellation law? No. We have to take one more step. VS1. So x plus 0 prime equals 0 prime plus x, which equals 0. Also, x. And also, x equals x plus 0, which equals 0 plus x. Then, by cancellation law, I can cancel x. I can cancel x here. Z is here, not here. So then 0 equals 0 prime. Okay, so that's why I don't like mathematics. 如果严格数学来说，这个地方是错的。我们还要用 v， 因为我们还没证明说，我们证明的 order 顺序是这个 x 加 z 等于 y 加 z， 我们没有证明 z 加 x 等于 z 加 y。所以我们没有证明这个，但是只是多一步，我们去交换它的 order。好，那在 VS1 已经提供给你这个可能性了。OK， so don't worry, it will not be in your examination. 好，我不会考试的时候不会让你们从 VS1 背到 VS8，然后要去那个要去证明说啊，它符合 VS1 到 VS8， 好，大概不会这么，因为后面有太多精彩的东西要你们证了。好，所以不需要这些东西。Okay, so here, correlate to the vector y described in VS4 is unique. Why is VS4? VS4 is that we have the additive inverse, and right now we will need to prove that additive inverse is unique. So here I'm not going to prove it because I will just leave it for your homework, for your self-study. And actually, whenever you see the proof request to prove uniqueness, use the contradictory approach. So then you will get the answer. Okay, so here the vector 0 in VS3 is called the 0 vector of V, and the vector y in VS4 is called the additive inverse of x, and which we denote is minus x. Okay, so both of them are unique. 0 and the additive inverse are unique. So then we're going to discuss theorem 1.2. Okay, so for theorem 1.2, in any vector space V, the following statements are true. The following three statements are true. The first one is that 0 times a vector x equals 0 vector for each x belongs to vector space V. And B, mass A times x equals mass A times x first, and then equals A times mass x vector. A times its additive inverse. So, okay, for each A belongs to a field, and for each x belongs to vector space V. And the third one is that a scalar times multiply 0 vector will be equal to 0 vector for all the scalar. So here we need to prove A, B, C. Now, so let's prove A first. So we want to prove that 0, the scalar multiplication of 0x equals 0. So we've got to use the property VS1 to VS8 to prove the theorem. So here we just use VS8. So VS8 says that, so let's go back to VS8. VS8 says that A plus BX, two scalar, we have the addition first, and then do the scalar multiplication on this vector, will be equal to AX plus BX. So now, we can apply this property. So 0x plus 0x equals 0 plus 0 times x. So this is VS8. Okay, and then 0 plus 0x equals 0x. So then we will apply VS3. 0x equals 0x plus 0. And then use VS1 to interchange the order of 0 and 0 plus 0x. And then by using cancellation law, I can cancel 0x here, 0x here, and I get 0x equals 0. Okay, so this is the way we prove that if we have a scalar 0 multiplied by any vector, then I will get 0 vector here in A of theorem 1.2. And for B, here, we want to prove this. So for B, here, first of all, we need to apply the definition of additive inverse. So we know that the minus x is the additive inverse of x. So we will have minus ax is the additive inverse of ax. Okay, so here, because minus ax is the additive inverse of ax, so I can write ax plus minus ax equals 0. We can simply consider this is vector y, and this is minus y. So they the additive inverse of y. So I can have this one. So that is VS4. So by this approach, that is VS4. And then we can apply VS8. So I can have A plus minus A times x. Okay, and then also, so we can have, so we can use the distribution law. We use the distribution law, so which will be equal to let's see, ax plus minus ax. Okay, and then this will be equal to 0x. Sorry, this will be equal to 0. Sorry, I have to use this one. Sorry. 0. Wait a moment. So that is for VS4. And also, maybe I will write it this way. Sorry. Equals 0. That is from VS4. And then from theorem 1.2a, 0 vector equals 0 times x. So that is theorem 1.2a, which we have just proved it. And then a 0 times x, then we will have a plus minus a times x. because A from the definition of field, A plus mass A equals 0. So then we can have AX plus mass AX. And then we can use the cancellation law here. Then we will have mass AX equals mass AX. Okay, the proof is quite tedious. And then we still need to prove that it will be equal to A times mass X. So what we are going to prove here is that, so right now I have A times mass X. So we can write it as A times mass 1 times X. So by Vs, which Vs I cannot remember. Okay, this one, Vs6. So by Vs6, we can have mass A times X. Okay, we can have mass A times X. So because mass A times X equals A times mass X, and it also equal to mass AX. So then we have this one. We have proof B here. We have proof B here. Okay, so now we prove B in the theorem 1.2. And the next, we will prove A times 0 equals 0. And the process, the proof is similar to A. So here, we define A times 0, because we need to prove that A times 0 equals 0. So here I have A times 0 equals A times X plus its additive inverse. Okay, and by using distribution law, AX plus A times mass X here. And then by using B here, it will be equal to AX plus mass AX here. And then by using distribution law times X, and then we get 0 times X. And 0 times X by using the first statement, it equals 0. So finally, we prove it, but which is very straightforward. Okay, so strictly speaking, we have to prove it by using all the 8 property and all the theorem we have already proven. Okay, so that is the theorem 1.2. Okay, next is subspaces. Okay, so right now we have already known the vector space, the definition of, and the properties of vector space. So right now we're going to discuss the subspace 子空间。好，我们把这叫子空间。我们有向量空间 V， 然后我们有子空间 W。Okay, so let's see what is the definition of the subspace. This is in the section 1.3 in the textbook. So here, definition, a subset W. Here right now, remember, we have the subset W, not the subspace yet. So a subset W of a vector space V over a field F is called a subset of V if W is a vector space. Note that W is also a vector space. Okay, W is also a vector space over field with the operation of addition and the scalar multiplication defined on V. So right now, we have a vector space V here. Okay, here V, I write it with one more line here, which means the boldface. 好，这代表出体字，所以只要是向量空间还有这个子空间，好，我们都用这个大写的 v 跟 w， 然后或者是 u。好，我都会在左边再加一笔，这代表 both phase， 代表的是粗体字。好，它指的都是向量空间或是线性转换。之后我们会讲 transform 是 t。好，那我会写这个样子。好，这个是一个线性转换，我不会只写这样 t。好，那这个因为在这个 notation 上面，我们要把它写成一个粗体字比较不好写，所以我会在旁边再多画一画，代表它是一个向量空间，代表它是一个粗体字。Okay, so here in V we have a definition of x, y, and we have a definition of addition and the scalar multiplication. So we have x plus y and the cx and also 0 because they are the basic components in a vector space. So now I have a subset of V, which we denote as W, and W itself is also a vector space. Without V, W itself is a vector space. So W is also a vector space. So in W, we have VS1 to VS8. But in W, because W is a subset of V, so all the addition, vector addition and scalar multiplication are subject to V, subject to the definition of addition and scalar multiplication of V. So the definition is based on V vector space. So here W itself is also a vector space. Okay, so if all the elements in W is also in vector space V, then W we call it as a subspace of V. Okay, so here we have to know that. So in W we also has a zero vector, but is this zero vector identical to the zero vector here in V? We don't know yet. But because W is a vector space, so 0 prime exists. We have zero vector in W. Okay, so here, so if we, with this kind of concept, so V itself is a subspace of V. Also, zero vector itself is a subspace of V. Okay, so both of them are subspace of V. And then we can just recall the definition of set and a subset. So if I have a set S, then a set of S, which means that it contains some element here. So why is a subset of S? S itself is a subset of S. And another one, empty space, is a subset of S. What does empty space mean? In this space, in this set, it contains no vector. So here, one thing is important. Is zero vector set equals empty set? The answer is no. Zero itself is still a vector. Okay? So 0 itself is still a vector. It's not an empty set. But 0 itself is a vector space. Zero vector set itself is a vector space because from the definition of vector space, 0 plus 0 equals 0 plus V0, V is 1. And 0 plus 0 plus 0 equals 0 plus 0 plus 0, V is 2, etc. Within this vector space, I have only one element, one vector. We have only one vector, which is 0. Which is 0. So this is the vector space, consists of only one vector. Okay, so 0 vector set is a vector space, but it's not an empty set. So please note the definition of empty set and a 0 vector set. They are not the same. Okay, so we have V is a subspace of V, and the 0 vector set is also a subset of V, and we call this one as 0 subspace. Okay, so we have a definition here. And so because we know W itself is also a vector space, so all the A properties hold. But as long as W is in V, W is subspace of V, then actually we don't need to verify VS1 to VS8. We only need to verify the following 4 properties. The first one is that if X plus Y belongs to W, if X belongs to W and Y belongs to W, then X plus Y belongs to W. That is the closure property under addition. Okay, and the second one is that if X belongs to W and the C is a scalar, C is in the field, then the scalar multiplication is also in W. So there is a closure property of scalar multiplication. And third one, W must contain a 0 vector, because W itself is a vector space. So it must contain a 0 vector here. And also, each vector in W has an additive inverse in W. So here, we want to use a diagram to represent it. So if I have a vector space V, and then whether W is a subspace, we need to prove that, we need to know that X, Y belongs to W, then X plus Y must be in this W. And also CX, scalar multiplication, is in this subspace 2 and also 0. Okay, and also minus X. But in fact, if A hold, if A is true, then of course additive inverse exists. Property 4 exists. Okay, so here property 4 is redundant. Property 4 is redundant, and also 0 vector of W must be the same as the 0 vector of W of V. So here 0 must be equal to 0 prime. Okay, so right now we need to prove these 2 statements. We need to prove these 2 statements. Okay, so we will prove the first one is redundant first. We will prove the first one is redundant first. So here I have vector space V and a vector space, a subspace W here, and we have X here. So if right now we haven't proved these three property yet, but we assume here the first 3 property hold, then we want to prove that property 4 is redundant. So if 1, 2, 3 are correct, then we have 0 vector in W. And this is the same 0 vector in V. So we will have, because 0 belongs to subspace W, and subspace W is contained in V. Okay, and also X belongs to W. So we let Y be the additive inverse of X, such that X plus Y equals 0. Okay, such that X plus Y equals 0. But because X, Y, okay, so Y be the additive inverse of X, so X plus Y equals 0. Then we know that Y will be equals to 0 plus minus X. So here, so Y equals 0 plus minus X. So because we know 0 and X belongs to W, then minus X, which is a scalar multiplication. So we have minus X equals minus 1 times X. So from property 2, X is in W, C is in the field, minus 1 is in the field. So minus 1 times X is in W. So this belongs to W. Then, okay, this belongs to W, this belongs to W. And then from property 1 here, it belongs to W, it belongs to W. So the sum of these two vectors belongs to W. So Y is in W. And Y equals minus X. Okay, so property 4 is redundant. Property 4 is redundant. And now we need to prove the next one. Okay, here we need to prove theorem 1.3. 1.3 is very important in this chapter. 1.3 says that let V be a vector space and the W is a subset of V, then W is a subspace of V if and only if the following three conditions hold for the operation defined in V. First one, 0 vector. 0 vector here in V must be contained in W. Okay, so 0 vector belongs to W, the same vector. Second, whenever X belongs to W, Y belongs to W, X plus Y belongs to W. And C, whenever C belongs to field, S belongs to W, CS belongs to W. Okay, so for any subspace, we need to verify whether A, B, C hold in this subspace. If A, B, C are all valid in this subspace, then it is a subspace. Okay, so here, but right now we need to notice that if and only if。好，那我们中文讲说叫做弱且为弱。那弱且为弱的时候 ，whenever you see if and only if, which means that okay, you must assume the statement here is true. We need to prove A, B, C. Then we need to assume A, B, C is true. We need to prove W is a subspace. So we have to prove it from the left-hand side to right-hand side, also from right-hand side to left-hand side, because of if and only if. 好，所以当你看到弱且为弱的时候 ，if and only if 的时候，那你就必须要首先你必须要假设上面的 statement 是真的，那你要去证明 A、B、C， 然后你要反证过来 当 A、B、C 是真的时候，你要反证这个 statement 是真的。好，所以它的证明会比较复杂一些。OK， 那 so let's first prove it from left-hand side to right-hand side. So we know W is a subspace. So because W is a subspace, so from left-hand side to right-hand side, W we have already known W is a subspace in V, but this statement also tells us W is a vector space. W is a vector space. So whatever vector x, y in W in the vector space, x plus y is in the vector space, and the cx is in the vector space. They hold immediately. Okay, because that is in the definition of a vector space. So B and the C, so here W is a subspace of V, and the vectors in W follow the addition and the scalar multiplication defined in W. Then B and C hold directly. So here B and the C has been valid already. But right now we want to know whether 0 prime equals 0. Okay, so we need to prove A, the 0 vector in V also in subspace W. So we need to prove it. Okay, so here, this is, so for this statement, it means that we have to prove uniqueness. We have to prove uniqueness. So to prove A, to prove A, because W is also a vector, it's a subspace, which means it's also a vector space. So right now we assume 0 prime is in W. 0 prime is the 0 vector in W. So 0 prime belongs to W. And 0 prime is not equal to 0. This 0 is in V. Okay, so now we have, because W is a vector space, so we have X belongs to W. X plus 0 prime equals X. That is VS3. Okay, so that is in W. Then, because X belongs to W, and W is contained in V, so it means that X is also in V. X is also in V. So then, in V, VS3 tells us X plus 0 equals X. So then we have X plus 0 equals X, and this will be X equals 0 prime in W. So here, this in V, is in V, and here is in W. Okay, so then we can find, if we cancel here, then we have 0 prime equals 0. So we can use the cancellation law. It's in W. Okay, so then which means that this statement is not correct. So we say 0 prime is not the same as 0 is not correct, because after the proof procedure, finally we find 0 prime equals 0. So this assumption is not true. So which means that in this vector space, V and W, 0 vector is common in both subspace W and the vector space V. Okay, so here we prove it from left-hand side to right-hand side. And the next, we need to prove it from right-hand side to left-hand side, which means that if A, B, C are correct, then W is a subspace of V. But here, because of the time, we cannot complete it today. So I will just leave it for the next Wednesday. So it's this is the end of today's class. OK， 好，今天就到这边，因为时间不太够证明后面的部分。